This is Math 5700 Lecture 34, and we're going to discuss section 5.41, which is about the binomial approximation, the normal approximation to the binomial distribution. Let's get started. So in order to motivate what comes next, I'd like to consider the following. This is off the internet, and I don't, usually this is animated, but somehow the person who animated it or the website which does the animation is dead. But here's the idea. Suppose I flip a coin, and the result of flipping, I go to the left if I get heads, and I go to the right if I get tails. And I suppose like repeatedly flip. So if I repeatedly flip a coin, eventually each flip I go down one row, I will end up somewhere. And if I do this over and over and over again, the most of the coins are gonna end up near the middle, and the shape of the distribution is starting to look like a bell curve. And that's the content of what I want to talk about today. So let me get started. Okay, so in what follows, I'd like to let phi of little z be the cumulative distribution function of z, which is a continuous random variable of type n01. So it's a normal random variable, and its mean is 0, and its variance is 1. So this is notation. Nothing more than that. Okay, so now here's the idea. Suppose we have repeated Bernoulli trials. If you don't like this language, just think of flipping a coin, a biased coin, where probability of a success is equal to p. So now let's let S sub n be the number of successes occurring in the n trials. So I flip a coin n times, biased coin, probability of heads is p. How many times do I get heads? That is a random variable. This is a discrete random variable. Okay, so let's recall when we talked about the binomial distribution, because this is actually a binomial random variable, the expected value of this is n times p, and the variance of this random variable is np times 1 minus p. Okay, so this is going to roughly be my mu in my normal distribution, and this is going to roughly be my sigma squared. Okay, so now let's consider the following thing. Let's consider the probability. So let's consider the probability. Okay, so now what I want to do is I want to normalize S sub n. So that is, I want to consider the random variable x sub n given by taking S sub n, subtracting its mean, which is n times p, its expected value, and dividing by its standard deviation, which is np times 1 minus p. So this is a normalized version of Sn. Okay, or it's called a renormalized version. Okay, so now I'm interested in computing. I'm interested in computing the probabilities associated with this random variable. So what is the probability that A is less than or xn is less than or equal to B? That's the question. Okay. So let me state the answer. So the answer is the probability that A is less than or equal to xn is less than or equal to b, where A and b are two constants, is given by the probability that A is less or equal to z is less than or equal to b, where z is a continuous random variable. This is not an equal. This should be approximately equal, and I'll explain what this means. For very large values of n, the probability of the discrete random variable xn is approximately given by the probability of an n01 random variable z being between a and b. In other words, this is the same thing as phi of b, the right-hand side, minus phi of a. Okay, so that's the answer. Well, it's partially the answer. The question is, what does this expression for large n actually mean? So what does that mean? That means as n approaches infinity, you'll get equality. You get equality. These probabilities agree, so that is the limit as n goes to infinity of the probability that A is less than or equal to xn is less than or equal to b. For each n, you get a different random variable, and this is going to be given by the probability that A is less than or equal to z is less than or equal to b. There's inequality now. So that's the answer. That's the answer. But the question is, so this is a limit. This is as xn, so you have all these random variables, x1, x2, etc., x3, etc. So there's a limit of different random variables. So now, when is this a good approximation? So p a less than or equal to z is less than or equal to b is a good approximation to p of a less than or equal to xn less than or equal to b if the following is true. If n times p times 1 minus p is at least 10. If we can verify this condition, then we may compute the binomial probability, which is on the left side. It's given approximately by a normal probability. So on the left side, we have a discrete random variable, discrete probability, and on the right side of the equation, we have a continuous probability. Okay, so let's see how this works in practice. So let's do an example. So example, let's flip a coin, a fair coin. So p equals 0.5, and we do it 60 times. Okay, so now let x be the number of times heads occurs. Okay, so I want to compute the probability that x equals, I want to approximate the probability that x equals 20. Now, since x takes only integer values, and this I'll explain in a moment why I'm doing what I'm doing now, we can also say that this is exactly the same thing, that x is between 20.5 and 19.5, since x only takes integer values. Okay, so since x is integer valued, this doesn't change anything. And this is called the continuity approximation. Okay, so now the reason I'm doing this is now I'm going to use the result on the previous slide. For this, we need to know what NP is. So N is 60, N times P is 30, and N times P times 1 minus P is 15 in our case, right? So therefore, when we normalize or renormalize, we're going to get X minus 30 over the square root of 15 lands between 20.5 minus 30 over the square root of 15 and 19.5 minus 30 over the square root of 15. In other words, this is the same. This is actually equal. It's not approximately equal. I haven't gone to the normal distribution yet. Now I go to the normal distribution. I get an approximately equal to the probability that, okay, so what is the left-hand side? If you compute 19.5 minus 30 over the square root of 15, you get negative 2.7 on the left. And on the right side, you're going to get negative 2.45. And so now it's an approximate. I'm using the normal approximation, the standard normal approximation. And so this is the same thing as phi of negative 2.45 minus phi of negative 2.7. And this is, if you go and look this up on a calculator, what this the values of these things are, you get 0.007, or you can go use a table, minus 0.003, which is 0.004. So that's the approximation that I wanted to get. Now the actual answer, if we use the binomial distribution to answer the question, the actual answer is 0.0036. So this gives a fairly good approximation. These are approximately equal, these two numbers. Okay. Okay, so if in what follows, I just want to talk about what correction rules we should be using. So if we have the probability of x equals n, the continuity approximation should be what we just did before. We add and subtract 1/2 from n, if this is what we're trying to calculate. If we want to calculate the probability that x is strictly greater than n, we would take, that means that it can't be equal to n. We would take n, add 0.5, and use the probability that x is greater than n plus 0.5, because x is integer valued. The first condition holds if and only if the second condition holds. If x is less than or equal to, let me try to see if I can clean this up a bit. Oops, I didn't do that right. So this is less than or equal to. So let me, oops. Yeah, so let me fix this quickly. Yeah, so this is the best I can do. So if we use less than or equal to n, x is less than or equal to n, then that would be the same thing that x is strictly less than n plus 0.5. Okay, so these are the various So these are the rules that we need to apply to correct. Okay, so with that in mind, I'm going to do a couple more problems. Okay, so suppose we roll a fair die 180 times. What's the probability a 3 will be showing more than 50 times? So here in this, the solution to this problem was like this. So here n is 180. The probability is the probability of a 3 occurring, which is 1/6 of the time. So n times p is 180 over 6, which is 30. And then np times 1 minus p is actually given by 25, because 1 minus p is 5/6. Okay, so therefore the square root of that is the square root of 25, which is 5. So now we want to approximate the probability that x here is the number of times 3 occurs. So we want to estimate the probability that x is strictly bigger than 50. But the continuity correction says we should be taking x greater than or equal to 50.5. That's the same thing. Okay, so now the probability that x is bigger than or equal to 50.5 is the same thing. We can renormalize. X is minus n times p, which is 30 over 5, is greater than or equal to 50.5 minus 30 over 5. In other words, and this is approximately the same thing as the probability that z is greater than or equal to 0.82. Okay, so this is the same thing. The latter is the same thing as 1 minus the cumulative distribution function evaluated at 0.82, which is the same thing as 1 minus 0.794, which is the same thing as 0.206. So that is the approximate value. Okay. So this is the solution. So suppose a drug is supposed to be 75% effective. It is tested on 100 people. What's the probability that more than 70 people will be helped? Okay, so let x, here's the solution, and we're going to use the normal approximation to the binomial distribution. So let x be the number of people helped by the drug. So this is roughly, this is a binomial random variable where n is 100 and p is 0.75. So n, which is 3/4, and np is 75, and np times 1 minus p is 18.75. So, and the square root of np times 1 minus p is the square root of 18.75, which is 4.33. Okay, so now let me work to the right here. What are we interested in calculating? We're interested in calculating or estimating the probability that x is at least strictly greater than 70. If we use the continuity correction, that's the same as the probability that x is greater than or equal to 70.5. And then we can normalize. That's the probability that x minus n times p, which is 75, divided by 4.33 is greater than or equal to 70.5 minus 75 over 4.33. And this is approximately equal to, by the theorem mentioned at the beginning, the standard normal z being greater than or equal to, well, the thing on the right, if you calculate, you get a negative 1.039. So this is then given by 1 minus the cumulative distribution function evaluated at minus 1.039. And this is 1 minus 0.149 if you calculate it on a statistical calculator, and that's given by 0.851. So 75, the probability that 70 or more than 70 people will be helped is about 85%, 0.85. Okay, let's go to another problem. Okay, in our last final problem for today, about 10% of the population is left-handed. Use the normal distribution to approximate the probability that in a class of 150 students, at least 25 of them are left-handed, and then in the other case, the other part of the problem is between 15 and 20 are left-handed. So here let x be the number of left-handed students. So this is a binomial random variable. Here n is 150, and p is 0.1 or 1/10. So what is n times p? N times p is 1/10 of 150, which is 15, and np times 1 minus p is equal to 15 times 9/10, which is 13.5, and the square root of that is the square root of 13.5, which is 3.67, approximately. So in the first part of the problem, we are asked to calculate, in part A, we're asked to approximate the probability that at least 25 are right-handed. So at least, which means 25 or more, and if we use the continuity approximation, that means that x is at least 24.5 because x is integer valued. This is the continuity correction, and then that's the same thing by normalization as x minus n times p, which is 15 divided by 3.67 is greater than 24.5 minus 15 over 3.67. And that's the same thing as that's approximately the same thing as the probability that z is at least, well, what is that fraction on the right? It's 2.58. So you get a 2.58, and that's the same as 1 minus the cumulative distribution function evaluated at 2.58, which is the same as 1 minus 0.995. So the answer is we're going to get is 0.005. So that's the answer to part A. Okay. Okay, so I have the parameters in on the left. I've just copied them over. And in part B of the problem, I'm just showing part B. We want to know the probability that between 15 and 20 are left-handed. So that's the probability that the number of left-handers, the number of left-handers is between 15 and 20. I'm having trouble with the screen here. So we're interested that x be between 15 and 20, and we have to use the continuity approximation so that 14.5 is less than or equal to x is less than or equal to 20.5. Okay, and so what do you get? Well, we normalize The normalization is, we have to take 14.5 minus 15 over 4.33 is less than or equal to x minus 15 over 4.33 is less than or equal to 20.5 minus 15 over 4.33. And this is approximately equal to the probability that, well, we can compute the numbers here. The first number is negative 0.136, sorry, is less than or equal to z, is less than or equal to 1.49. So now this is the area under the standard normal curve between negative 0.136 and 1.49. That's this region indicated here in yellow, which is the same thing as the probability. That's the same as phi of 1.49 minus phi of negative 136, I should say. And that's the same thing as 0.932, that's, I've used the calculator, minus 0.446. And what do you get? The difference is 0.486, about 49% of the population of the class, 150 students, 48% are actually probabilistically left-handed. And that's all for today.